this video, we are going to talk about electrophilic aromatic substitution reactions of benzene, which is chapter 16 in our textbook. We studied in our previous chapter that benzene has 6 pi electrons, as a result of which it makes the ring quite stable. It's aromatic in nature, and it follows the Huckel's rule of 4 and pi electrons. That's 6 pi electrons. Benzene is a highly stable molecule, and unlike other alkenes or unsaturated hydrocarbons, it does not undergo addition reactions. So, for example, if you had a cyclohexene type of molecule, and if you react it with a halogen like chlorine, recall that we did this last semester where the pi bond would open up and we get an anti-addition of chlorine. So it shows addition reactions. However, if you take benzene and react it the same way with chlorine, and we expect it to open up like the previous molecule, will chlorine add to it in this manner? No, this reaction does not take place. Why? Because here we had 6 pi electrons, highly stable. Here we have 4 pi electrons, unstable. Correct? So this reaction does not take place. What kind of reaction does benzene show? It shows a substitution reaction where it retains its aromaticity. So you can substitute hydrogens on the benzene ring with electrophiles. So that's why these type of reactions are called as electrophilic substitution reactions. So EAS, that's what we abbreviate this type of reactions. EAS, where E stands for electrophilic, A stands for aromatic, and S for substitution. So no addition reactions, but we see substitution reactions. The reactions that we will see in this video lecture are very similar, all have a very similar mechanism. The only thing that you will see a change is in the type of electrophiles. Okay, so let's list the type of reactions that we are going to see here. First is halogenation, where the benzene reacts with halogens. It could be chlorine or bromine, so I'll write X2, where X stands for chlorine or bromine. This reaction actually takes place in the presence of Lewis acid, where again the Lewis acid can be a FeX2 type of molecule or AlX3 type of molecule. Okay. The resultant is a substituted product where the hydrogen has been substituted by the halogen. Here, my electrophile, E+, is a halogen which is either Cl+ or Br+. Okay, so X can be Cl2, X2 can be Cl2 or Br2. Okay, the second type of reaction we will look is nitration, where again the mechanism is going to be very similar to the previous one, except that now the electrophile is NO2+, and to generate that, the reagents we will require are HNO3 and H2SO4. The electrophile here would be NO2+. So benzene gets substituted by NO2. So again here we can keep on drawing the hydrogen, which is the one that is replaced. Third type of reaction would be what's called as sulfonation. Here the electrophile is SO3H, and to generate that we will need H2SO4, concentrated H2SO4. And this would result in sulfonation of the benzene ring with a SO3H group. And here my electrophile is an SO3H plus. Okay, again look, we have all the electrophiles with a positive charge on it. The next reaction, which we will look in this chapter, would be Friedel-Crafts alkylation. Friedel-Crafts alkylation. Here the electrophile is an alkyl group. So R plus, where R stands for any alkyl group. Okay, so benzene reacting with an alkyl halide, right, RCl. Again, this takes place in the presence of a Lewis acid like AlCl3, resulting in substitution of the hydrogen with an R group. And finally, the fifth reaction that we will look is Friedel-Crafts acylation. Friedel-Crafts acylation, where the electrophile is now an acyl group, which is represented like this, RCO plus. Okay. Benzene reacts with the acyl chloride in presence of Lewis acid again, where the hydrogen is substituted with an acyl group. So these are the 5 reactions that we are going to look. As I mentioned before, they all have mechanisms which are very similar. The only thing that is different in each of these reactions is the formation of the electrophile. Okay? Because every reaction has a different electrophile. So let's look at the mechanism for each one of them. Okay? But you will see the pattern that except for step number 1, where we form the electrophile, the other steps are very similar. Okay? So we'll start with halogenation. And we can put the heading mechanism. All right. First step in this reaction, again, maybe we should write down the overall reaction just for you guys to remember what is really happening in this. So we take the benzene, and I'm going to use chlorine as my example, and I'm going to use aluminum chloride as my Lewis acid. The overall reaction is where the hydrogen is substituted with chlorine. Step 1, let's do the mechanism. Chlorine, which can be written like this, acts as the Lewis base and donates its pair of electrons to aluminum chloride, AlCl3. It's a Lewis acid base reaction where the chlorine reacts with AlCl3 to form a complex where there is a bond between this new chlorine that's coming from the Cl2 with the aluminum. Okay, so maybe we can use color here. I'm going to identify this chlorine with a different color, right? Okay. Now I'll keep these chlorines intact, which were the original chlorines on aluminum. And then we have a new bond that is formed between aluminum and the chlorine here. All right. Now, when this complex is formed, this chlorine will get a positive charge because it has donated its pair of electrons to aluminum. and aluminum gets a negative charge because it has accepted the electrons from the chlorine. So we'll put a negative charge here. So this is my aluminum complex, aluminum chlorine complex. Because chlorine is more electronegative in nature, it's going to pull off these electrons towards itself, as a result of which this chlorine here gets a positive charge. Okay, so in the next step we can think of this giving off an AlCl4 minus, correct, because this whole part gets separated. These electrons are pulled by the chlorine, and we result in an electrophile which can be drawn like this. Right? So this electrophile is the one that would be my, which would be reacting with benzene in the next step. Okay? So this electrophile that we obtained from the previous step. Then the next step, benzene reacts with the chlorine plus opens up its pi bond to form a complex. Here again we call it a sigma complex, and here again I'm going to use a different color to show that one of these bonds, let's keep this pi bonds as blue color, okay, that one of these pi bonds opens up to form a bond with chlorine. Okay, so this carbon, which was using this pair of electrons to fulfill its valency with the neighboring carbon, now is short of electrons, so it gets a positive charge. This is called as a sigma complex. Okay, this is called as a sigma complex. So now the benzene ring has lost its aromaticity, because instead of the 6 pi electrons, now it has got only 4 pi. However, it can stabilize itself by resonance. This sigma complex stabilizes itself by resonance, and we can draw the resonance structure. How? By moving this or delocalizing this pair of electrons, and the charge gets distributed at different positions on the benzene ring. Okay? So here we can look at the 3 carbon atoms on which this delocalization would happen. So 1, 2, 3 here. We can redraw the second resonance structure, where pi electrons move over here. This bond remains intact. We still have the chlorine, the bond with the chlorine. Here I would mention that I'm going to keep on drawing this hydrogen atom, because ultimately that's the one that's going to be substituted. So it's a good idea to show the hydrogen atom, even though it is understood. Even if we do not draw, it's understood there is a hydrogen atom there. I'm just going to draw, because in the next step we will see that this hydrogen will be removed by the base. Okay? All right. So here is my second resonance structure. So see how the charges are charge is moving from here, this carbon atom, to here. And now we can draw a third resonance structure where the delocalization of electron happens between these 3 carbon atoms. We draw the third resonance structure for the sigma complex. So this bond remains intact. Now our pi electrons move over here. We have the bond still with the chlorine atom. Okay. And the positive charge would be now at this carbon atom, right? I will still keep my hydrogen. So these are the three resonance structures which stabilizes the sigma complex. So we can think that benzene opens up its pi bond to make a bond with chlorine, loses its aromaticity, but at least it is being stabilized by the different resonance structures of the sigma complex. Okay. Now comes my third step, where this proton is lost and the aromaticity is regained. Okay, so we can write step 3 on next page. Step 3 would be benzene with its so I'm going to pick up one of the sigma complex. Okay, I'm just leaving the colors aside. This is one of the sigma complexes. You can pick any one of the sigma complex to show your last step. It doesn't matter which one you choose. So one of the sigma complex resonance structure I picked up, and where I have the positive charge in this carbon. Finally, we get rid of the proton here so that we can regain the aromaticity on benzene. And for that, to remove the proton, we need a base. And what would be the base? The base would be the aluminum chloride, or AlCl4 minus, which was generated in the first step, correct? Where we had the AlCl4 minus. That's the one that's going to take up the proton and then put these pair of electrons back here, and that gives me back my benzene, or the substituted benzene, right? So we keep the 3 pi bonds here, and the proton has been removed, and now we get the substituted benzene. So that's how you have to follow the mechanism for halogenation. And you will see that the other reactions also follow the mechanism in a very similar manner. Only difference would be the formation of the electrophile in each case. Okay, let's do one more, which would be nitration. I'm going to use a different page to show nitration. So we are doing second reaction, which is nitration of benzene. Okay, always the best way to study all these reactions would be to write down the overall reaction first, so that you know what exactly is happening. So we take benzene. For the nitration, the reagents that you will need are HNO3 concentrated and H2SO4. Okay, so for nitration, we need HNO3 and H2SO4, both strong acids for the formation of the electrophile, which is a nitronium ion. Overall reaction, where the hydrogen in the benzene has been replaced by the nitronium ion, NO2+. Okay. So in this case, this mechanism would be first step, formation of electrophile. And for that, we need both of them. So we have HNO3. So HNO3 can be written like this. N double bond O, O, okay. This is how HNO3 is represented. Okay. So if you see, we have a negative charge here and a positive. Okay. The formal charges, if you put, this oxygen has a formal charge of -1. This nitrogen has a formal charge of +1. This is the lowest structure of HNO3. This actually reacts with H2SO4, where we can again write H2SO4 in this manner. Both lowest structures, these are called as oxo acids. The lowest structure of H2SO4 is represented like this. Okay. Now in the first reaction, what happens is nitric acid actually acts as a base to react with this acid, sulfuric acid. So it's a little different reaction, because we always know HNO3 as an acid, but relatively speaking, sulfuric acid is stronger. So this acts as an acid, and HNO3 acts as a base in this reaction. Okay, so what this oxygen is going to take this proton, acid-base reaction, put these electrons over here, and we get an oxygen which has now 2 hydrogen atoms still attached to the nitrogen, double bond to this oxygen, single bond to this oxygen. Okay, so nitrogen still has a positive charge, But now look what has happened. Since this oxygen from nitric acid took a proton from sulfuric acid, this H2SO4, this oxygen is going to also get a positive charge, right? So it looks like this is a very unstable compound because we have two positive charges right next to each other. So what will happen is we will lose a water molecule, right? So this oxygen is going to take the pair of electrons from here and produce water molecule H2O. See, this is H2O. It generates, in that process, it generates the electrophile, this one, with nitrogen having a positive charge. And then we also have the side product, this one, the remaining part of sulfuric acid, which is HSO4 minus. Okay, so these are all the components of this, or the products in the first reaction, right? So let's go back and review it one more time. In the first step, nitric acid, this is HNO3, acts as a base. Oxygen grabs the proton here. This is acting as an acid. Sulfuric acid is acting as an acid. If it makes it more clear, we can again put color here, right? So I'm going to color this sulfuric acid's proton, which is going to be removed in red color. So nitric acid takes that proton. So say this is my proton here. However, you can see that when oxygen takes an extra proton, it gets a positive charge. Unstable compound because we have two positive charges right next to each other. So this really wants to take up the electron pair from this bond. Nitrogen gives it off, but at the same time, this oxygen gives off two electrons here to form a double bond, and we get the electrophile in here. Okay, so this electrophile is deficient in electrons here at the nitrogen atom. So that is what we need in order for benzene to react. Okay, this electrophile is actually called as nitronium ion. In addition to that, water molecule will be formed because water is removed from here, H2O, and then HSO4 minus is from this part, from the sulfuric acid. Okay, so the remaining part of sulfuric acid is given off as HSO4 minus. Okay, so we won't worry about the other products because we only need nitronium ion from our first reaction to continue the next. So continuing the reaction with benzene now, we have benzene reacting with the NO2 plus, which was formed in my first step. Okay, you can write down the complete Lewis structure with all electron pairs. Double bond opens up to react with nitrogen atom. Okay, so here is my nucleophile, which is benzene. Electrophile is my nitronium ion. This is step 2. Okay, step 2 in my mechanism. Similar to halogenation, if you recall, one of the bond opens up, so that forms a bond with NO2 now. Okay, so when this happens, we have to give back the pair of electrons here. So NO2 is attached to the benzene ring. At the same time, this carbon atom gets the positive charge, right? This is again my sigma complex. This can undergo resonance stabilization, where again we will move the positive charge on the ring, at the same time moving the pair of pi electrons too. Okay, so we have benzene ring here. The pair of electrons go over here. The pi bond moves here. We have this pi bond intact, and now the positive charge is here. I will still keep my hydrogen drawn in each of these structures, so that in the end I can show the deprotonation step. Okay, so we have the second sigma complex resonance stabilization. Here we do the third one, where you move the pair of electrons between these two carbon atoms, and then the positive charge is on the other carbon. So we keep this intact. We have pi electrons move over here, positive charge goes over here, NO2 is still here, and the hydrogen. So this is my resonance stabilization. Resonance stabilized sigma complex. Finally, in step 3, we can pick up any of this sigma complex. Pick up the first one, doesn't matter which one you pick. Okay, so I'm picking the first sigma complex which I drew with my NO2 there and the hydrogen. Now this is the step where the acid-base reaction would take place. We need to remove this proton. So this acts as an acid. What will be the base here? Base would be the HSO4 minus, which was generated in my step number 1. Okay, so the remaining part of sulfuric acid, which was HSO4 minus, that's the one that's going to take up this proton. It's acting as a base, it's acting as an acid, and now putting this pair of electrons back here to regain the aromaticity, and we get the final substituted product with hydrogen being substituted by the NO2. Okay, so and then my side product would be H2SO4. So this is the mechanism for nitration. So as you see, let's go back quickly and review. What we did in nitration. Step 1 was generation of the electrophile, which is the nitronium ion. Step 2, reaction of benzene with the nitronium ion, formation of the sigma complex, which is resonance stabilized. And then final step is where the aromaticity is regained by removal of this proton by the base, and you get the final product, nitrobenzene. Okay, so in this manner, you can continue doing the mechanisms for the rest of the reactions. In a separate video, I'm going to talk about sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation.